Okay, hello. Thanks for inviting me to this great place. I'm Gyeongsik and working at Meta. Today I'm talking about towards 3D interacting hands recovery in the water. So we humans interact with world through hands. And there could be various types of interactions, and we actually interact with various types of objects. For example, guitar is designed to be interactable with our 5 fingers, and the door, we can grasp the handle and turn the handle to open the door. Or we express our feelings or intention with hand gestures like this. So this kind of interaction is not actually limited to physical real world, but it's extended to virtual world through AR applications. So motivated by this importance, many 3D hand assessment methods have been introduced. Early works actually try to make tests easier, take depth maps as an input, like starting from random forest-based approaches, and the 3D CNN-based approaches have been also introduced, which utilizes large-scale depth map data sets. But obvious limitation of using depth map is that it requires additional sensors like depth cameras or stereo cameras. So for real-world applications, the community switches direction from depth-map-based one to single RGB-based one, because people can easily take single RGB inputs with their mobile phone. RGB dataset and fragment dataset contributed to this single RGB-based approaches so long. So let's summarize how the community has changed. First, starting from depth-map-based one, the community switched the direction to RGB-based one. So this could be seen as using unrestricted input, because RGB is definitely more affordable data for people to get using a single mobile phone. But let's create the other axis, unrestricted hand motion. So at that time, there was some assumptions on those methods, like the input should contain only a single hand, and the input should be hand-focused one. So it's time to investigate the other direction towards unrestricted hand motions. For this one, we have very unique keyword, interaction, which makes hand very distinctive from other human parts like body and face. There could be various types of interactions. The first type might be interaction between objects. We humans interact with various types of objects, and this is very challenging because of two major factors. The first one is that, as the figure shows, hand is mostly occluded by object, which makes 3D hand reconstruction greatly challenging. The other thing is contact. We need to accurately recover contact between hand and object, but this is very challenging because we need to make a balance between attraction and repulsion. If the algorithm is biased to attraction, there could be more collisions between hand and object. But if the algorithm is biased to repulsion, then there is no collision, but there should be no contact. And recently, there have been introduced some data sets like introducing object interaction between object and tool hand, like assembly data set and RT data set. And what I want to talk in this talk is interaction between hand and hand. So we often make hand-to-hand interaction when, for example, having some random chatting with our colleagues, or even with some special meeting like a pray. Because of it's very challenging. I mean, similarity between all fingers of two hands and occlusion, it makes this task greatly challenging. So this makes early works take decimal as an input instead of single RGB. The primary reason of taking decimal was the lack of RGB-based data set. So to address this, we actually introduced our InterHand data set, which is the first RGB-based data set, large-scale data set, which consists of two interacting hand images and accurate 3D ground truths. Let me first briefly introduce our InterHand data set. So our InterHand data set consists of two types of sequences. The first one is pixels, which is a transition from neutral pose to predefined hand pose, like a fist, and transition back to neutral pose. It contains like extreme poses with maximum band or extended finger to include all the corner cases as well. But peak pose alone is not enough because it is artificially created one. So to capture some natural hand motion, we capture additional sequence called range of motion. It has some conversion gesture with minimal instruction, like telling subject to wave hands as if telling someone to come over. In this way, we could capture diverse hand poses and major hand poses as well. And the major challenge is annotation. How can you annotate this kind of greatly challenging two-hand interaction? So our annotation pipeline consists of two stages. The first one is manual, and second one is automatic. For the manual annotation, we show some 5 to 6 views to the annotator, and when annotator annotate 2D hand key point of 2 views, then our annotation tool automatically triangulate them to 3D space and project back to remaining views so that the annotation could be performed in a relatively consistent way. However, there are so many frames in our data set, it is basically impossible to annotate all of those frames. So this is the reason why we introduced automatic annotation, which uses, so first we train strong 2D key point detector on our human data set, and then test on all remaining frames. And then we perform ransack-based triangulation to back project the 2D key point to the 3D space. As our data set has about 100 viewpoints, our triangulation is very robust, and the annotation error is about 2.78 millimeter, which is quite low. And this figure shows the importance of new interacting hand data. So when a regressor is trained only on single hand data and tested on 2-hand data, it performs very bad. But the regressor is trained on both single and interacting hand data, it performs really well. So that shows that our newly captured 2-hand interaction is necessary to understand and analyze interaction between 2 hands. And this talk will introduce our 2 approaches for 3D interacting hand recovery in the wild. The first one is algorithm side, and second one is dataset side. So after introducing our InterHand dataset, there are many attempts to recover 3D interacting hands from single RGB image, which is good. But most of them have only shown their results on InterHand dataset, not on InterWild dataset. So one observation we have for the 3D interacting hand recovery in the wild is that we have very limited number of 2D interacting hand data. So this graph shows that we have only 8K 2-hand images in MS Focal, while we have 70K single-hand data in MS Focal. That means even although they only provide 2D data, we have a very limited number of 2D interacting hand data. So then let's say we train a regressor on this data set. Then as we have a number of interacting hand data in InterHand, the mini batch will look like this. So mini batch, half of the mini batch comes from InterHand dataset and remaining half from MS Focal dataset. But InterHand dataset has 2-hand images. So that makes images from interacting InterHand dataset and MS Focal have different 2D scale space. The 2D scale is the average of height and width of each hand. And the right figure shows that as 2 hands are included in a single image, 2D scale of each hand varies a lot, like this. But 2D scale of single hand image is always constant, 1.0. So this kind of 2D scale gap makes increases domain gap between 2 types of data sets. So to address this kind of domain gap between 2 data sets, we change our mini batch simply like to this one. So that all inputs are in the shared 2D scale space so that we could reduce the domain gap between this kind of 2 types of data sets. Another observation is that although they have very large appearance domain gap between these kind of 2 data sets, their geometry domain gap is very small. So motivated by this, we design our network to regress 3D relative translation between 2 hands only from geometry inputs, so that they could not suffer less from domain gap between 2 types of data sets. Let me show some overall pipeline of our regressor called InterWild. So from the human image, we detect hand boxes. And then SHNet takes a single hand image, regardless of whether two hands are interacting or not, so that inputs are in the shared 2D scale space. And next one is transnet, which regresses relative translation between two hands. And it takes only 2.5 bit, which is geometry feature, so that transnet suffer much less from the domain gap between InterHand dataset and InterWild dataset. Final interacting hands is obtained by moving left hand mesh using the estimated relative translation between two hands. And this qualitative result shows effectiveness of and robustness of our approach. So this second row is interesting example. The left hand is totally observed by the right hand, but ours successfully recover. There is some collision actually in here, but ours actually recovers some reasonable two hands, while existing work totally fails to recover two interacting hands. And this is also an interesting example. So the right and left hand looks almost the same because they have almost the same hand pose. But ours successfully separate two hands and produces some robust result, while the previous one fails to. And this is me. This is taken with my mobile phone, and this also shows the robustness of our regressor. There are some collisions actually, like here. If you see closely, there are some collisions, but overall, it produces some reasonable result, which of course needs to be improved. And another direction that I want to address the robustness to in-the-wild environment is in the dataset side. So let me introduce our very recent dataset called InterHand dataset, which is a dataset of relighted and 3D interacting hands, which is accepted by NeurIPS this year. The basic concept of this dataset is using relighting network to enhance diversity of using track geometry. So this is the relighting network that we use to render two interacting hands. This relighting network paper is introduced in this year's CVPR, and this is from our Meta Pittsburgh office. So let me first compare four types of datasets. So InterHand dataset, let me call it a lab dataset because it is capturing a lab environment. Image object diversity is very low because background is always black and illuminations are from uniformly installed LED. Panel colors are like a greenish, so diversity is not good and far from InterWild images. But appearance is realistic. Realistic means it looks like real human hands compared to this one. Compared to this one, it looks like real human hands, right? And ground truth 3D pose is diverse, yes, because we capture a lot of hand poses using peak pose and range of motion. And the other type is, let me say, the natural data set. The appearance diversity is limited. So natural data set is captured with a very simple setup, like using a single Kinect or stereo camera in front of desk. So appearance diverse is not very diverse because it's captured in front of desk. Like it is not captured from swimming pool, concert hall, only captured from a single place. So appearance is realistic and close to indoor environment. But ground truth 3D pose is not diverse because it is captured with very simple setup. So complicated hand pose could not be annotated with this setup. Ego 3D hand has diverse appearance because background is brought from random images, but appearance realistic is not good and far from indoor images. And ground truth 3D pose is diverse because it's a rendered one. So our data set is to address somewhere between this kind of data set and this data set. So appearance is diverse, yes, because we use a number of environmental map. And ground truth 3D pose diverse, yes, because we capture new interacting hand captures. But this is not yes, but not no. It's somewhere between this one and this one. So this shows all the publicly available 3D hand data set, and only very few have two hand interactions. And InterHand dataset and HRC dataset are the most widely used one because RGB2 hand is too small, and Ego 3D hand has some not good image quality. Of course, there are some datasets that have two hand annotations like Agora, H2O, Arctic, but they are not for hand-to-hand interaction. This graph shows that. So let's say average of shortest distance between two hands. They have very long distance between two hands. That means hands are separated like this. They are not interacting each other. So HRC InterHand, re-InterHand data set have very short distance between two hands. And also contacting sample, ratio of contacting sample. Igora H2O Arctic, they have a very small amount of contacting sample, which means hands are separated like this. But our HRC InterHand, re-InterHand data set has like this kind of many contacting samples like this. And this shows post TSNE comparing our data set, our new data set, and InterHand data set and HRC. Ours has very diverse hand poses. We captured new interacting hand captures. So our data construction pipeline consists of two stages. First one is capture stage, which is exactly the same as what we did for InterHand data set. And using the asset from the capture stage, we use pre-trained relighting network to render images with environmental map. And one important thing is accurately tracking pose. So previous InterHand data set performed triangulation from estimated 2D key point, but we found this is not enough because triangulation, ransack-based triangulation, could select some different viewpoint, even though frame is very close. So that could result in very differing 3D hand key points, especially when hands are severely interacting with each other. So using our virtually postnet, which is my previous publication, we achieve very accurate and stable 3D key point allocation. So here, key point is very differing, like this, but ours produces very stable and accurate results. So this is what we did for accurate annotation. And we only captured 10 interacting hand captures. We only should have 8, but we are now rendering 2 more now. And the good point of our data set is that we could render egocentric viewpoint with simulated test throw camera. So as far as I know, there is no egocentric data set that has 2 interacting hands, and ours could be the first egocentric viewpoint data set. At the same time, we have third-person viewpoint as well. And this shows, these are from capture stage, and this is from relighting stage. So this background is very changing for every frame. So based on this geometry asset, we render relighted images like this. And what to release? Our dataset has 3 assets. First one is 1K image, and second is foreground mask, and the third one is monoparameters. The foreground mask is newly added one compared to InterHand dataset because many people ask me foreground mask for the neural rendering stuff. So now we can develop neural rendering techniques using our real InterHand dataset because we have foreground mask like this. And we are going to release 4 versions. Third-person viewpoint, frame-based one. All frames have different environmental map, but same frames with different cameras share the same environmental map. And for the video research, we also release renderings where same segment have the same environmental map. And egocentric have the same content as well. And this shows the effectiveness of our data set. So we train a regressor on various types of training set. The first one is training on InterHand MS Coco data set. And there are other variants like training additionally on capture state data set and composite and adaptive install normalization and our relighted data set. Only our relighted data set decreases error on HIC, which means our is much more beneficial than other alternatives like this. Especially this kind of composite adaptive install normalization do not have realistic appearances. For example, when we change the light, skin color should not change. When we go to ski, when we play ski, my hand does not change to white color. But this kind of simple RGB-based, pixel-based normalization changes my skin tone change my skin tone very different skin tone. So that could, and there's no light consistency between foreground and background, but ours have satisfied all these properties, which is the reason why our regressor achieved better results on HIC data set, which is a natural data set. And yeah, let me introduce my future research. Maybe I think one obvious future research should be integrating full body 3D human reconstruction and interacting hand. Especially this could be useful for, as previous speaker Kuvaro said, sign language recognition or generation, because there could be so many hand-hand interaction in sign languages. Also, there could be many cases where this kind of integrating full body reconstruction and interacting hand at the same time is very important. Yes, this is my talk, and please ask me any questions if you have. Thank you.